Hello. So we are going to consider an interesting example of a panel data set. So this is about traffic death and alcohol taxes. So whether if you put higher alcohol taxes, then would it prevent traffic accidents? And even if not, still there won't be a negative effect. Higher higher alcohol tax would not cause an increase in traffic accidents. So that's what we are going to check with the data. So here, let's think about the data structure first. The observational unit is United States state by a year. So by a state by a year, we observe the number of death tolls, number of deaths, traffic fatality rate as a ratio per 10,000 residents, and we also observe tax on beer. And so there are 48 states, and we observe 7 years. So 48 states, maybe excluding Hawaii and Alaska, maybe, and 7 years from 1982 through 1988. So the total number of observations is 336. It is balanced, perfectly balanced. Every state is observed over 7 years. And in the data set, we have additional variables like legal driving age, drunk driving laws, but we focus on these two relationships. The effect of beer tax on traffic fatality rate. As I said, I would expect a positive or negative relationship. So higher tax should imply no effect or negative effect on traffic fatality rate. Let's think about the data. This is the data. So here, suppose that you don't know how to handle panel data. So even if there are 7 years data from 7 years, you don't know how to handle the time dimensions. So you delete all the things, all the other years, and only use 1982 data. So it's cross-sectional data. This is just 48 states in 1982, and then if you run a regression, it is positive, which means higher beer tax causes higher fatality rate. It doesn't make sense, right? Like if you pay more tax on like drinking, but you are making then you should drink less, and so there should be fewer traffic accidents and fewer traffic deaths, which is our that's our conjecture, but the data shows something different. It may be insignificant, but it's positive. What's going on? So we are going to explain why this problem happens. In the end, we will have a negative effect. I will explain what was the problem, and then I will explain how we get the negative effect as we expected. So let's think about this. First, let's think about in maybe. So I believe it is wrong. It cannot be true. It cannot be positive. So there may be some omitted variables. Some important variables are not included in the analysis, such as quality or age of automobiles, and quality of roads, and culture about drinking and driving. How generous toward drunk driving, and like the density of cars. Like of course, crowded area, like a rural area, is more safe, even if you drive under influence. So anyhow, these kind of character. Of course, there may be more, but these are some of important factors which was not considered in our analysis. Then think about now. Let's think about the omitted variable bias. How the bias can arise. So first, think about traffic density. So think about New York City, the difference between New York City and a rural area. Uh, obviously, high density, high traffic density implies more traffic accidents. Obvious, right? And at the same time, like rural states uh, tend to have lower alcohol tax. Um, I don't know why, but it's clear tendency, observed tendency. So then, so then, lower alcohol tax is correlated with lower traffic density, and lower traffic density is correlated with lower traffic accidents. So lower alcohol tax looks like correlated with lower traffic accidents. So so they have positive correlation. So this is one possible reason why the graph has a positive slope, right? So exactly this is the omitted variable bias, and this is how we guess the sign of the bias. Um, and then now, like later, I will explain this can be removed. This can be fixed easily by panel data. Second example, similar culture toward drinking and driving. Say where in the region where they are more generous toward drinking and driving, then obviously they will be more generous in beer tax. So usually where like in more generous areas in generous cultures, there will be more traffic accidents because there will be more people who would drive after drinking. At the same time, maybe politically or their consensus would be lower tax. So this is another like another omitted variable bias, but in this case the direction is the other way. So lower beer tax means more generosity toward drinking, and then that causes uh, higher like more accidents. So in this case, the correlation is negative, and the bias would be uh, the other way. But anyhow, so there are different factors causing different types of omitted variable biases. All of them, combining all of them, you see this as a result. Then how can we remove them? So ideally, if you observe traffic density, if you have data about that, include that. Or if you can observe culture, then include that as another regressor variable, another control variable. But that's not easy. So then what we are going to do here is, before doing that, just imagine uh, a variable zi. So this is state i's unobserved variables such as traffic density and culture toward drinking. And what we assume here is it does not change over time. So traffic density is about like urban planning, like it's city planning. So like the density in New York City and the density in a rural area, uh, like they stay pretty stable. They must be stable over time, at least within 7 years that we observe the data, right? Within the 7 years, it won't be there won't be a huge drastic changes in traffic density. Similar in culture. Culture even it would be even slower to change. So we assume that culture, traffic density, and like say quality of roads and all the other variables are included here with the under the assumption that it does not change over time. Say it does not change over time, right? Then simply let's think about 2 years. We only consider 2 years, simply the beginning of the observations in 1982 and and the end of the observation 1988. if you consider these 2 years and assuming that, pretend as if you observe z, the time consistent, the persistent characteristics of the state, then 88 regression equation is above, and the below is 82 regression equation, and everything else is the standard, like say peer text and controls. And what we are going to do here is subtract the bottom from the top. Then what we want here is we can cancel out these two guys. So zi will be canceled out because it does not change over time. So the value of z, value of the culture does not change between 82 and 88. So their effect must be the same. I don't know how much is how large the effect is, but I don't care. They will be canceled out. And then in the end, it doesn't matter even if you observe it or not. Even if you do not observe the z, still you are fine as long as you can cancel them out. So what we are going to do here is we observe now our equation is like the change in fatality rate between 88 and 82. So the change in fatality rate is regressed on the change in beer tax. So it's now a new regression with change and change. So change on change regression, or difference in difference and difference regression. So then now you do not need to observe z. This is the key idea in panel data analysis. Using this idea, you may remove a lot of omitted variable bias without observing them. So this is, and another important thing here is, of course, the intercept is canceled out. Intercept beta 0 will be canceled out. So when you estimate this regression, so you have to remove the constant from the regression model, and which means the intercept should be 0, because if there is no change in beer tax, according to our model, the fatality rate should not change, because there is no other factors that change over time and that cause any change in fatality rate. So that's a simple way to fix the problem. And let's see how it works. So I'm showing, so this is the regression model if you use 82 data only. 82 data only, you have a positive coefficient, even if it is insignificant, but still it is positive, which is weird enough. And in another separate regression, now using only 88 data, you get again a positive slope, which is more significant. It's actually very significant. This is a bigger problem. It is now significantly positive. It cannot be interpreted like using our intuition. But now this is the solution. So difference, take the difference and take the difference. Here the intercept is not removed, but it does not matter. So anyhow, change in fatality here, and here change in text, and then the relationship is minus 1.04, which is significant. So isn't it interesting? So like year by year regression gives you only positive results, positive coefficients, but when you take their differences, then the coefficient becomes negative. The reason being this guy. So z was not canceled out in a single year regression, but you have to cancel them out by taking the difference. That's the big thing. So including the intercept does not cause much problem. Here anyhow it is insignificant. It's very close to 0. So it is insignificant, so does not cause much problem. It's your choice. So this is the result. Now if you use more than a single year, then you have this, and intercept is here. So here is 0. When the beer text change in beer text is 0, then the change in fatality is also close to 0. Okay, this is a very interesting example. So I will explain more about this model and more general model, how you can generalize this idea to multiple years and more rigorous setup. Okay, thank you for watching. See you later.